The first speaker today, after Dale's briefing, is Dr. David Novak. David is with the Hydrometeorological Prediction Center, and he's also the chief of the development and training branch there. So we have a little bit of a video to show you before David starts his presentation. So let's go ahead and take a look at that.
I'm David Novak, and I work at the Hydrometeorological Prediction Center, and I'm chief of our development and training branch. HPC is the nation's go-to center for heavy precipitation and medium-range forecasts to support a weather-ready nation. Our particular focus is heavy rainfall, heavy snowfall, and forecast out to 7 days. One aspect is to provide national guidance to the local offices, say, what particular modeling systems or ensemble solutions might be best for this particular region of the country. We also are in direct communication with the local offices as well as the river forecast centers to provide kind of that expertise of the forecast situation. We also provide gridded data to these local offices that they can use as their starting point for their local forecast. As you may know, flooding and flash flooding is a leading cause of weather-related deaths and cause on average up to $7 billion in damages across the United States. And so it's a real key societal impact. Of course, these extreme events are rare, and by definition. And so it can be very challenging to get the exact location of these extreme events, especially with lead time. Oftentimes we know that there's the possibility of an extreme rainfall event, but exactly when and exactly where is really challenging. And so that's where we're investing in new science and new communication capabilities as well as new services to improve the public's awareness of what we know when we know it. So we've seen with Sandy, Irene, Isaac, the Duluth flash flood, that these extreme rainfall events really can have significant societal impacts. And the Weather Service is there for you to both, through our science and service, to help communicate the message and to help really save lives and property and protect lives and property from these extreme rainfall events.
Well, good morning. I really appreciate the invitation to come out here, Dave. I really appreciate the opportunity and the other organizers. What I'll be talking about today is advancing extreme precipitation science and forecast services for a weather-ready nation. And I want to point out, this is not just my work. There's a whole active community looking at this very critical challenge, and a number of their names are pointed out here. So first, quick question, and I think somebody already knows, but anybody know what the, well, I didn't realize we didn't have it on the screen yet. It's going to be really hard to answer. Sure. There we go. Anybody know where this background image comes from? And it's got to be someone else, because yeah, Nashville. A really historic flood there. This is an interstate, believe it or not. Yes, yep, in 2010. May 1st, 2010, just a tremendous flash flood. So these are the types of events I want to address today and how we can better forecast and improve our services. So we'll talk a little bit about the motivation and background. We'll then move into what the Hydrometeorological Prediction Center can provide. And then I want to really get into the meat of the talk, which is the science and service gaps. Where do we need to improve to really address these types of situations? And then we'll talk about different aspects here of how we can make these improvements. And if there's one thing I can leave you with today, it's the need to think probabilistically, to the need to communicate that, these extreme rare events do occur and there is these possibilities. So this will dovetail quite nicely with Greg's talk yesterday. So flooding is a leading cause of weather-related deaths. On average, flooding claims more than 90 lives and causes more than $7 billion in damages annually. And man, has the nation been assailed by these extreme events. From Nashville, Arkansas, the Duluth flood was just amazing, some of the images coming out just last summer. And so there's a need for quantifying and communicating the threat of these rare but devastating and deadly events. So we'll take a quick look at some of the climatology aspects here. This is a plot from Ralph and Dettinger, which shows the maximum 3-day precipitation totals at co-op stations over about the past 60 years. And the gray dots here, you're already starting at 8 inches. So even parts of Nevada and the interior west can get these really massive amounts of rainfall. But the real critical areas of the nation are the west coast, where you can get greater than 20 inches in kind of a 3-day period. And then along the Gulf Coast here is kind of that secondary hotspot. Of course, it's not just the amount of rain, but it's also the vulnerability and what the soils can handle. And we'll talk more about that. In terms of the climatology, you can see that it's really a western U.S. challenge in the cool season. If you go by the month here, so January, February, that's about their maximum with these atmospheric rivers that come along the coast. And then the eastern United States starts to ramp up and reaches a peak during the hurricane season. So the nation has a whole variety of extreme precipitation events. And one way to visualize these extreme precipitation events and kind of the seasonal cycle is to look at that top 1% of the rainfall amounts. So a colleague of mine, Ben Moore from the Esro lab down in Boulder, he looked at the percentage of those top 1% events over the nation by season. So for example, here we are in wintertime, and you can see over the west, almost entirely all those extreme events occur during the winter. And some of them occur, out in the southern Mississippi Valley, just as we had last evening. As we move on into the spring, almost anywhere in the nation can have, one of these top 1% types of events. And then something interesting happens in the summer, and you might expect. It's really a Great Plains issue with the MCSs into the northern plains as those MCSs kind of roll around the ridge, those ridge rollers, and that you can really get the devastating floods. And then you start to see the southeast U.S. pick up as we start to get into the hurricane season. And then during the fall, actually parts of the Intermountain West with the, particularly in the September timeframe, the residual of the monsoon, and then along the Gulf Coast. And so you kind of see this evolution of these extreme events through the cycle. So just to focus real quickly here in the western U.S., it really is about the atmospheric river. These are the primary driver of the extreme precipitation, the flooding, and the water supply in the western United States. So an atmospheric river is a narrow corridor of very strong water vapor transport. And when these, colloquially called rivers reach the coast, of course, they hit the terrain, and you have ascent, and you can really get some extreme rainfall amounts out of these features. Just a quick stat here that might be kind of interesting. The average atmospheric river transports the equivalent of over 7 times the discharge of the Mississippi River. That's a lot of water, and of course directed right at that terrain. And indeed, if you look at the total seasonal rainfall, these atmospheric rivers can account for on the order of 30 to 40% of all the precipitation in the West. So a major, major feature. As we move east, it gets a little bit more complicated. This is a plot from Schumacher and Johnson, which is showing that the east here is dominated by these convective storms, the mesoscale convective systems, particularly in the summertime. And then we move on, throughout here you have these synoptic scale events that are kind of just a background event. They can occur almost any time of the season. And then finally, during the tropical season, of course, you can get a contribution from those tropical systems. So this is just kind of a neat plot, again, by Ben Moore at Esro. He's plotting here over the last about decade all the different tropical systems that affected the area from North Carolina southwest to Louisiana. And you can see, and then he added up all the amounts of rainfall from those systems. And you can see North Carolina has been particularly hard hit the last decade. But these tropical systems really are a key part of the precipitation climatology and extreme precipitation climatology in the southeast U.S. Okay, so I want to transition here a little bit into where I'm coming from. Brand new facility on the research campus of the University of Maryland. It's called the NOAA Center for Weather and Climate Prediction, and it is a beautiful, state-of-the-art 21st century building. It really is becoming the nerve center of the weather enterprise here. Within this building, we have a number of National Weather Service units, such as the Environmental Modeling Center, where the critical modeling data comes from, the Climate Prediction Center, Ocean Prediction Center, and NCEP Central Operations. We also have the portions of NESDIS, so the satellite folks working directly in the same building as the numerical weather prediction folks, and then the Air Resource Lab from OAR. So it's meant to be kind of a synthesis of the NOAA resources here for weather and climate prediction. So within this unique environment, HPC is situated. And in our real vision here, we want to be America's go-to center for these high-impact precipitation events and to provide this forecast guidance out to 14 days for weather-ready nation. That is our key vision, and I think we're really, as you'll see, I think we're really moving out on this and making a difference here. So just briefly here, you know, HPC, I think you particularly probably think of the rainfall and the winter forecast that we provide. We have a number of other operational desks, such as our medium range desk, which provides guidance out to 7 days. You might have read our model diagnostics discussion, kind of a blog, if you will, of as the guidance is coming in, of what the forecaster is seeing with that guidance, kind of hedging one way or another. Our short range forecast, the surface analysis. I always joke when I give tours, you have the surface analysis there and say that they produce the surface analysis every 3 hours for eternity. I mean, every 3 hours for the foreseeable future, you know, we'll be producing a surface analysis across the country. And perhaps you didn't know, but the HPC does serve as the backup to the National Hurricane Center. So we take that very seriously, are very engaged with close connection to the National Hurricane Center so that we're able to take over in a heartbeat if we're asked. So our key constituent has traditionally been internal. It's really been the field offices providing the guidance that they need to provide the best local forecast, other NCEP centers, and federal and state agencies. But I think through time, certainly over the past decade, we've become, I think, much more public and have interacted much more with the media community and private sector and aviation. Just this past year, we reached over 1.5 billion hits. Perhaps that's not as impressive as the Weather Channel, I know, but for a federal agency, we're pretty proud of that. And if you consider the hits by a desk, QPF is certainly our most popular product, but the basic weather, just kind of these kind of simplistic charts that just give a quick summary, really are quite popular, as well as the surface and the medium range. So a whole suite of weather information. But again, what I'm here today to talk about are these really extreme precipitation events. So I want to focus on our QPF desk. So you're probably most familiar with our deterministic QPF. And so we'll talk a little bit about that, but I want to expose you to some of our other products here, including the excessive rainfall outlook. Before I do that, I just want to point out kind of the forecast process. You know, how do we produce these QPF forecasts? And, you know, of course, as you're probably aware, it varies by the forecaster and phenomenon. But going to go simple here. And maybe I'll ask a question. For heavy rainfall, what are the 3 ingredients that we need for heavy rainfall? I'm sorry. Rate. Okay, interesting. I guess I'm thinking more simplistically. Moisture. Okay. Lift. I heard lift. These are, well, moisture, lift, and instability. So, I mean, but you're right that you can look at it a different way in terms of the rate and the duration. I mean, that's obviously another way of looking at it. So there's a multiple, variety of ways to look at this. But, if you have the ascent, if you have the moisture, and if you have the instability, you're going to get some pretty heavy rainfall. And so this is what forecasters are looking at. They're first looking at the observations, and then just simplistically, they're looking at the model and ensemble forecast of these particular elements. And then, I was just talking to Dale here over breakfast, and I think we have a similar approach where we're kind of doing a selective or weighted consensus of this guidance. The human is involved here in kind of hedging towards one particular ensemble suite or another to kind of weight the different solutions. And they do this through, a whole variety of features: pattern recognition, physical realism, known model biases. You might remember the GFS precip bombs. You'd get these real convective-looking, vorticity maximums and kind of outrageous precipitation maximums. That was kind of a past model bias. It's been corrected about in the past couple of years, more or less. But forecasters could use that knowledge to kind of adjust the QPF. Past model performance, the trends, and collaboration with the local WFOs. And that's, I think, a unique aspect of HPC is this interaction between the National Center, which kind of has this broad view, and then the local office, which knows their particular topographic feature or such that might enhance the rainfall. So that's the forecast process. So what I want to look at is how this desk and the precipitation services that we provide is handled during these extreme events. So we're going to look at two deadly floods that occurred pretty recently here. The Nashville flood in May 2010, unfortunately, took 26 lives in Kentucky and Tennessee. And then more of a more flash flood here in Arkansas at the Cato Gap campground, where another 20 fatalities were taken. So these are some pretty nasty events. So what I'm showing here is what you're most familiar with, the deterministic QPF. So on the upper left here, we have the Nashville flood. This is a forecast 48-hour total of a 1 to 2 day forecast total. So on the order of a max of about 8 inches here. On the right here is this Cato Gap flash flood. The flash flood occurred right about where my cursor is there. Now, one thing with the deterministic forecast, it's a most likely area average. So we should expect, occasionally higher or lower amounts within those areas. And it's a most likely forecast. We're trying to provide, okay, here's our best guess at what the amounts over an area will be. So, of course, there can be errors. And I've shown here on the bottom here the observed. And you can see, the maximums here were almost double what was forecast in the maximum. You can also see some issues with displacement errors here, and also features that were just simply not forecast. So they may alert you to these general areas of the threat, but often the magnitude is too low. And indeed, if you take a look at our bias over the last decade, as you go out to these higher thresholds here, the 3, the 4 inches, we're roughly 2/3 of what occurs. So the deterministic QPF has limitations. So that brings us to the next product here, this excessive rainfall outlook. This is the categorical probability of exceeding flash flood guidance at a point. Very analogous to the SPC convective outlook. That was actually the intent of this product. So it has two key inputs. On the left here is the River Forecast Center flash flood guidance. This is the amount of rainfall that will saturate the soils. So any additional rainfall beyond that point could result in flash flood. And then, the forecaster has their QPF in mind, and they know that it can be higher. And so they try to quantify that so far in kind of a subjective way, with just kind of outlining the slight, moderate, and high risk of excessive rainfall. And so the slight, we've calibrated this to what we're actually forecasting, and it turns out that when the forecaster draws a slight risk, there's only about a 5% chance, but it's basically at a 5-kilometer grid box spacing. So it's basically your neighborhood. You have a 1 in 20 shot of your basement being flooded, and you probably want to know that. So even though it's kind of a low threshold, that's a pretty high impact event. The high here is on the order of 15%. So as we go back to our our flash floods here, these again were issued at pretty short lead time, but I'm just showing what it might look like in one of these extreme events where hopefully we'd have a high out, and it's very similar to the SBC convective outlook where we're trying to identify the region most at threat. You can see, for example, for the Arkansas flood, we had a moderate risk out, but we were too far south. And actually where the flash flood occurred was up here. We did note that, well, there could be about 5 inches, possible in that region. But the flash flood guidance, it turns out, the soils were quite dry. And so, there was kind of this trade-off between, well, it's going to rain a lot, but the soils are dry. And so there's always these aspects going into the forecast. So the point here is that, okay, this can help. It can identify these regions, maybe draw that slight risk a little broader than what the deterministic forecast is going to provide, but it's not a full picture of all the possibilities. So that kind of brings us to some of these science and service gaps. So if we take a look at the threat score, this is a measure of our performance over the past basically half a century here at the HPC. The higher the score, the better the forecast. The day one here is in the red, and you can see arguably over the last 2 decades, we've actually accelerated some of our improvement for this 1 inch and 24-hour threshold. We report to Congress our performance, and it's through this threat score. 0.31 was our goal, and we met that in 2012. Another thing to point out here is the day 3 QPF forecast is about as good as the day 1 was back in the mid-90s. So that's really a testament to the improvements that we've seen in the science and the modeling and just in our field of the improvements here. It really is pretty amazing and a good news story. But I added a but up there. And when you start to look at heavier thresholds, the 2 or perhaps the 4 inch in 24 hours, these are the ones that matter. These are the ones that cause those devastating flash floods. And if you look over the past decade, the 1 inch and the 2 inch have been improving. The 4 inch, it's been improving, but not at the same rate. It's at a slower rate than you start to see this gap start to develop here between the 4 and the 2 inch. And so that's certainly something that we want to address. The other thing, by the way, it's not that skillful. The 4 inch here, you have a threat score, basically pretty low, 0.1, 0.15. That's on the borderline of being skillful. So there's some real challenges here with the extreme rainfall. So just to kind of illustrate this challenge, and again, this is kind of simplistic, but might be a little fun. This is a 500 millibar height and vorticity map from a famous flash flood. And I just want to know what state do you think this famous flash flood occurred in? And all I can provide you is the respect of your colleagues for getting it right. No candy bars. No. Colorado. Why do you say Colorado? And admittedly, this is simplistic. Obviously, you'd want to look at precipitable water and all these other aspects. But indeed, this was the Fort Collins flash flood in 1997. You see just kind of this weak, southerly flow. There was upslope flow at the lower levels along the west side of the high. Let's try another one here. What state? Getting close, close. That's close. Arkansas. This actually is the Cato Gap flood. I guess I'll say 19 flash floods, but this was a mesoscale convective vortex, and it was heavy rainfall associated with that. We'll do one more here. The Weather Channel was particularly affected this day. Yeah, well, so this was the Atlanta flash flood. And, you can see, if I go back here, just this kind of weak, southwest flow at 500. So kind of your traditional, it's not going to scream at you for many of these types of flash floods that we're looking at. So let's move on here. So, yeah.
and the actual devastating flood occurs with one, say, convective burst after many days, right? So how do you face that challenge with respect to these 24-hour, categorical or outlooks? I think that's another aspect
Sure,
of this.
the time frame of the precip completely matters. I mean, you can have, if you have the heavy rainfall in just a 3-hour period, that can do it. That can cause the flash flood. So, yep, that's a good point. We'll get to some of the probabilistic aspects here. So on the upper left here, I have a kind of variety of extreme precipitation hazards: atmospheric rivers, the MCSs, tropical storms, nor'easters. Which of these do you think is the worst forecast feature, has the least predictability? So atmospheric rivers, MCSs, nor'easters, tropical storms. Yeah, right. We did a 5-year study looking at the HPC verification here, and threat score is shown here. The atmospheric rivers are, at the scale that we forecast, kind of this 32-kilometer scale. I realize, you can really get some real fine-scale details and it can be really challenging. But at this broader scale, atmospheric rivers are pretty well forecast with a bias near 1. Tropical systems, same thing. They actually, are, the track improvements we've seen, rainfall is, to first order, somewhat associated with the track. But the real challenge comes in the warm season, and that's those 500 maps that I was showing you. Those were all warm season flash floods. And you can see how, subtle, you aren't going to be able to necessarily pick it out from a 500 millibar map of where those flash floods are. I mean, frankly, we're terrible at these warm season convective events at these higher thresholds. So that's where I want to spend the rest of the focus here, is how are we going to improve these warm season, really hard to predict flash flood events. If you look at the improvement that we've had over the past 60 years, the cool season, December, January, February, it's just improving right along. Man, it looks pretty optimistic. But if you just separate out, June, July, and August, this is for the 1-inch threshold, and of course it'd be more depressing if we went lower. There's been very small, slow improvement. And so this, I think, as a weather community, is where the focus ought to be with the extreme precipitation hazard. Well, turns out this isn't a new aspect. Back in 2004, on the cover of the AMS bulletin, Ralph et al. In 24 had the summer rain dilemma, steps to improve warm season QPF. And what they noted was it really is a multifaceted problem. As you can expect, you need the best observations that you can get. And I know Clark, he talked about the dual pole. I think that is going to help in terms of having a better idea of what those observed rainfall amounts are. Of course, we've seen improvements in satellites. We're getting into unmanned aerial vehicles sampling the atmosphere. So there are some really kind of neat things going on. Data assimilation. This is the process by which you take those observations, put them in a format that a model can understand and use, and then it is used to improve the model forecast. So that's a really key aspect. And actually, NCEP is on the cusp of implementing what's called an Ensemble Kalman filter, which we think will be a pretty dramatic technological improvement to how we do data assimilation. And then you have to get to actual modeling in the Ensemble system. Resolution matters, the physics matter, and the configuration of these ensembles that Greg was pointing out can certainly matter of how you develop that probabilistic information. And then post-processing, I think Greg, again, showed some really neat examples of how to kind of summarize the vast array of ensemble information into something a human can understand and communicate. So the critical needs that they identified here were using probabilistic approaches, improving these models and ensembles, and communicating the uncertainty. And so what I want to do for the rest of the time here is really focus in on these three aspects, how we can improve these needs. So we'll first talk about using these probabilistic approaches. About 2 or 3 years ago, HPC actually went out with our probabilistic QPF. So this is probably a newer product that you may not be as familiar with, so I want to spend a little bit of time on this. what's really neat, one of our developers, Keith Brill, came up with an approach that uses that human deterministic forecast, the one that we've been used to for over half a century. Forecasters are used to creating it, using that and combining it with the new Ensemble information that we're getting. And so if you were to take a look at a graph, for example, of probability increasing and QPF increasing to the right, and the HPC deterministic forecast will always be the highest probability outcome here. So let's say this is 1 inch, for this amount. That's what the HPC forecaster was generating. It would have the highest probability. The spread, or the shape of that curve, is determined by particularly the Schref ensemble system. So in this hypothetical example, there was some members way out on the tail here, of having some extreme precipitation amounts. And so you can adjust that curve such that the HPC deterministic forecast is always the highest probability, but that shape is determined by the ensemble information. So a combination of the human with the ensemble. You can then derive, your probability of exceedance, your percentile information. So percentiles are kind of a way of thinking about breaking up the distribution. I'm going to point out this 95th percentile. So this is way out on the tail. What that's saying is there's only a 5% chance of exceeding that amount of rainfall. So I like to term it a reasonable worst-case scenario. You don't necessarily want to, go way out to the, the 99th percentile. I mean, you'll probably be in error, quite a bit of time. But this can provide users with kind of a reasonable approach to thinking about what could happen. 1 out of 20 chance of happening. So, here's an example. This is from our webpage. Along the left, we've added this PQPF, probabilistic QPF link, and it'll take you to this web interface. And this is actually from the Christmas Day event with all the tornadoes. There was actually some pretty heavy rainfall associated with that event, and some marginal flash flooding. So I wanted to take a look at that event. Here was our deterministic QPF. This was a 3-day forecast. This was issued, 3 days before the event. And you can see in general here we're 1 to 2 inches in kind of the deep south here. One of the interesting things of this case was St. Louis and Chicago. Note that they're dry in our deterministic forecast. Now, it was cold enough for snow in these regions. And so if you just went with this forecast, well, you're fine. Christmas Day, day after Christmas, no issue. But if I show you to the right here, this is the probability of exceeding more than ½ inch of liquid equivalent. And note that St. Louis here has on the order of 40% chance. So maybe a 1 in 3 shot at a pretty good snowstorm. You don't have that information with the deterministic forecast. But by having this probabilistic information, you can quantify that your viewers in St. Louis, for example, had a 1 in 3 shot of getting some snow in a key critical time, of course. So here's what was observed. Turns out St. Louis stayed pretty dry. Actually, it was a pretty good 3-day forecast here. But the amounts, were on the order of 2 to 3 inches in some of the deep south here. And so if I continue on to, here's the probability of 1 inch, here's the probability of 2 inches, there was on the order of maybe 5 to 10% chance of getting those 2 to 3 inch observed amounts. So, it at least provides the heads up that the most critical heavy rain area here was, Mississippi and Alabama in this case. Now, I talked about this percentile. This was the 95th percentile product for that particular event. And again, there's only a 1 in 20 shot of amounts exceeding this amount. So, it's kind of this reasonable worst case scenario. But, you can see even Chicago had a 1 in 20 chance of getting in on the action here. And these higher amounts, which were observed in the purple, are shown here with this 95th percentile reasonable worst case scenario. So it's a way to kind of, put in context that deterministic forecast, what is possible. This has really taken off. There's the hydrologic community is starting to use these forecasts, inputting them into their hydrologic models, and to kind of provide a spectrum of the observed flows on major rivers. The graphics we can use, in briefing emergency managers. And, this 95th percentile, you get this situational awareness of what's possible, this 1 in 20 shot of what could happen. So let's go back to our case examples here. On the left here, well, actually, yeah, so this is the Nashville flood. And on the left here, I have the deterministic forecast that we were seeing. And I want to point out these two areas, within the action and outside of the action. Here's what was observed. Of course, we underdid the maximum, and we completely missed this convective event out in Missouri. Now, obviously, the main action was here in Tennessee. Now, here's the 95th percentile forecast. Again, this 1 in 20 shot, and it's showing the max, it at least was getting closer to what was observed in this extreme event. It also was saying that there was this possibility of heavier rainfall, not quite as heavy as what was observed, but this heavier rainfall back into Missouri. So yeah, I think we have a question.
Do you think, or
well,
why is that?
Well, partially resolution, partially the predictability. I mean, these extreme events by nature are rare, and I think it's partly initial conditions of how the models are initializing these features. It's a whole variety of those critical aspects, the observations, the data, the models, the ensembles. It's hard to really pinpoint one particular aspect that's a silver bullet. I don't really think there's a silver bullet here. I think it's a whole combination of improvements. And we'll talk about that real briefly here. Yep.
So this analysis is all about probabilities based on ensembles, correct? So, and you pointed out that some events are more difficult to predict than others. And I'm wondering if you're learning which ensemble members are better for different regions and event types, and whether that can influence your interpretation of the data, or perhaps even how you build the ensembles from the members.
Yeah, well, and what we'll get to here is these new Stormscale ensembles, these 4-kilometer resolution type ensembles. I think they are the future for these convective type events. So resolution is a key aspect. But in general, you're not going to be able to pick particular members or family of members. That's the nature of the problem. I'm basically going to say no, that that is the nature of the problem. It's a probabilistic problem. We got to get away from thinking about that best deterministic solution. Any one model one day performs well. The next event may not perform well the next event. So, one more question here.
Yeah, let me just ask you a more philosophical question. People could argue, for example, that we just need to put more money into computers in order to, get the resolution up and get better models and all that stuff. What I'm hearing from you is that while that will help, there's also the human aspect of this, that people actually looking at this plays a large role. Could you comment on that? Because I think that's an important message for where we're going in the future.
Yeah, I'll just briefly go back here. I think it's worth. Yeah, I mean, the improving models and ensembles is a critical need. There's no question. So investments in NWP and the computing are critical. There's no question. But you're right also that in terms of communicating and interpreting what the information from that investment is another critical need. And we'll get to that here later in the talk.
Back to Ned's question about the individual members. You don't really want to pick out individual members, like you said, but how about calibration? How about bias correction in the ensemble? That is something that's shown some real promise. So
yeah, I mean, that's another approach that you can use. Now, bias correction, just like any algorithm, will fail in certain instances. And these rare events, of course, they're rare, which means you really don't know the performance of individual. It's rare to have these events. So the performance, you just don't have that long record. So bias correction, I think you know, it could help, but it's a whole spectrum.
Well, again, it only goes so far, and the rare event is naturally a low probability.
Right. Yep. Yep. This is another nasty case here. You know, if you look at the circles here, you know, we completely missed this event out in the panhandles here. Now, it probably wasn't the flood. I mean, the main flood was Arkansas, no question. Here was this 95th percentile, and in this event, yeah, it bumped up the precip a little bit where it occurred, a little further north. The max was not nearly what was observed, and the 95th percentile had, you know, there's no chance of a mesoscale convective system out in the panhandle. So the point here is that if the human doesn't see the event, and these ensemble systems, they still have errors. They still will miss these events, and in that case, you're gonna miss these events. So that points out that we really need to make some of these improvements that we're talking about. So let's talk about the models and ensembles. And so this relates to what we were talking about, the hope of high resolution. We know that parameterizing the convective processes, the turbulent ascent and updrafts, is a source of error. We're not explicitly modeling that. We're kind of getting the bulk properties of the temperature and the fluxes and such, and that's a real source of error. So what the community has done, of course, is as computing has allowed, we're getting down to these scales of roughly about 3 to 4 kilometers. And we're finding that you can improve, you know, the system character and improve the diurnal cycle and movement of these convective systems by getting the resolution down to these scales. So you can have some really spectacular forecast successes when you do this. This is an example of an amazing derecho that went through the central United States. This is a 25-hour forecast on the left. So this is the observed on the right. You can see the nice bow echo there, which was captured in this 25-hour forecast about in the right place. Wow, that must be the solution, right? Another good example here. This is the RAP forecast on the top here, rainfall activity on the left, wind gust on the right. This is of the derecho that went through the Ohio Valley into the mid-Atlantic. And the observed is on the lower panels there. That's pretty good. I'll just let that play through. You know, this is about a 12-hour forecast. Now we're getting towards about a 15-hour forecast. Of course, as you probably know, you can have some pretty bad forecasts too. On the left here is the observed radar, and looks like the loop didn't quite go here, but that's okay. We can jump to the precip. You know, here's the observed precip. This is in the 6 hours just prior to the flash flood. But you know, in this 30-hour forecast, there's no clue. Now, you know, it had an MCS here out towards Oklahoma City, south of Dallas, you know, some activity into Mississippi. But this is the challenge: is you can't get too lulled into, you know, thinking that these beautiful plots are reality. And indeed, even today, the average error of an MCS in a 24-hour forecast is on the order of about 100 to 150 miles. So, you know, locally here, you know, that's you think the big event's going to occur in the Denver metro. Well, it occurs up in Cheyenne. You think the big event's going to occur in D.C. It occurred up in Philadelphia. This is just in a one-day forecast. So this is a real challenge, and it's the nature of the challenge. So forecasters have been looking at this. We've integrated some of this high-resolution data in, and we know that you can get, you know, the improved visual of the movement of the convection, whether they're going to be supercells, lines, training echoes. You get these realistic amplitudes of the precipitation. Topographic signatures really pop out. But there's generally been a high bias of QPF. They actually go overboard oftentimes. And again, you can get lulled into thinking it's truth just because it looks good. The forecast details look very realistic, but you know, they may not occur. So, you know, this moves towards Greg's talk here. You know, what if we ensembled these different high-resolution runs together? So here's that event. This was one member. But if we ran, say, 20 members, and we're outlining here in this kind of spaghetti plot, outlining, you know, 2 inches in 6 hours. That's going to, actually it's a 1 inch in 6 hours. you really get the sense that, man, a lot of these members were targeting west central Arkansas. And so that may provide more confidence that, flash flood watch would go up, even though you have some members that are, completely saying there's no chance. It really is a power of ensembling these high resolution runs together. Just briefly, here's another Oklahoma City flash flood event. This was June 14th. 2010 was quite a year. In the operational SHREF, this is the probability of 2 inches in 6 hours. An 18-hour forecast. You're within that 24-hour forecast, and it was, approximately no chance. If you ensemble these 4-kilometer runs together, say you had 20 of these different runs together, this is what the folks at the Oklahoma University, the CAPS program, are doing. Here you see, almost centered right at Oklahoma City, a 50 to 70% chance of 2 inches in 6 hours. Now, I think they had more than 2 inches in 6 hours, but it's highlighting this particularly vulnerable region that you're not seeing in the operational guidance. So there really is this power of the storm scale ensemble for these convective precip events. Sure, question. Yeah. There's actually not necessarily. There are about 21 members in the SHREF on the left and about 20 to 25 members on the right. It's just the resolution is different. And you're not parameterizing, you're not estimating the convective impacts, you're actually modeling those updrafts and the change in latent heating and all these aspects. So, particular resolution here was a key aspect. So, Greg again talked about the hazardous weather test bed, and these test beds have really grown throughout the community. In INSEP, almost every service center has a test bed. The idea here is, you can test these new research concepts in an operational environment. It really is different when you're in an operational environment, when you have the time constraint, when you have the, just all these different operational constraints. And so they're embedded within the operational unit, so the researchers can kind of understand the advantages and challenges in operations. And I think we found that you can transition these new advances more quickly. So just schematically, these test beds kind of sit in the middle between the research side and the operational side. So the key test bed for heavy precipitation is the hydrometeorological test bed. And the focus here is to improve and extend prediction of these heavy precipitation events. And I think there's kind of two approaches here. You can better understand these features, what makes a training MCS versus not a training MCS, but also the improvement of this high resolution and ensemble guidance. And so you can test these new data sets, develop these new tools and techniques, often on the fly, through this interaction between the researchers and the forecasters sitting in a room trying to forecast events like the Arkansas flood, and you see the real challenges and some of the advantages. And it also serves as training the forecasters and the researchers, kind of this cross-training between the new science and the operations. So within our test bed, we basically have 3 focuses. The warm season QPF is a key focus, and I'll focus on that here. Just yesterday, we started our winter weather experiment. We do this annually. We bring in forecasters from all over the country and researchers and focus on winter weather challenges. It's looking pretty dry, I understand, the next week or so. At least we had a couple of events here. And then we also have atmospheric river events, these experiments. So these are kind of our 3 focus. I'm just going to move on here. So for the QPF aspect, again, you have forecasters, researchers, model developers, all in the same room, trying their darndest to look at the real-time, operational problem of the day, use these new tools, and integrate it in with what they're used to using. And you really get this neat synergy or interaction. The forecaster may say, well, the researcher may say, well, why don't you take a look at my new, this new model? The forecaster might say, well, because it didn't come in. Hasn't come in yet. And so you kind of get that education. So anyways, the details here aren't necessarily important, but it's through this process where these teams would kind of develop experimental forecast, and through that process evaluate the forecast and have these interactions. So we're going to kind of put you in the test bed environment here. I don't know if many of you remember You Make the Call from the late 80s. Yeah, okay. So this is the observed QPF, and what we do is, after the event, we rate, whether the particular guidance was good, fair, or poor. So here was observed. Here was the NAM. So I don't know, what's the consensus? Good, fair, or poor? Yeah. Okay. Here's one of these high-resolution members. This is from EMC, a 4-kilometer high-resolution run. What do you think? Yeah. Yeah. And here's another one of these high-resolution runs. Now let me really get at you. Which one do you think is better, the EC, EMC ARW up here, or the NSSL? Why? Right. So there's no right answer. And it's through these interactions. I mean, if you're in Northeast Texas, I mean, maybe if you're back here, I mean, I don't know, maybe, it's kind of this subjective discussion, and you start to get at, what is a good forecast, and you start to see some of the biases that come out of these different runs. But, so that's kind of the example here. We'll do one more example of an ensemble system. What's the key difference you see here between the operational guidance on the top here? This is the probability of greater than an inch. And then this new 4-kilometer Stormscale ensemble probability greater than an inch on the bottom. I guess there's two kind of big differences here. Yeah, I mean, it's entirely a state difference in the probability. Also, yep. Oops, sorry. Well, yes, it was. And you can see the further south solution occurred. Yeah. Oh, okay. Well, the question here was which of these, what's the difference between these probability products? And you can definitely see that it was basically a state difference in the location of the probability maximum. And the probability maximum in the new experimental Stormscale ensemble was much higher, which ended up being quite good. So I'm showing you mostly some of the good things. You do this for about 5 weeks, and you get a more, you get a nice sample, 5 weeks of, 5 days a week, so that's 25 different cases you're looking at, bringing consensus of both researchers, forecasters together. And, we had a whole variety of whether it improved upon the NAM or improved upon the SREF or didn't. This is the SSEO, that Stormscale Ensemble Opportunity that SBC now has the webpage. It, for QPF, did really well. And, for severe weather as well, as Greg was showing yesterday, did very, very well. But the point is that even among these ensemble systems and deterministic runs, the skill really did vary. Just because you went to high resolution didn't necessarily mean that you were better than the operational system. So there are other aspects at play. We also tested visualizations. You're probably familiar with these spaghetti plots, but what about if you plotted the maximum from any particular member over the whole domain? And that's what's shown here in the lower left for this case. What if you kind of smoothed out the probability of a particular event? And that's kind of the lower right here. And through that, then you'd get subjective impressions of the forecasters of what they liked and what they didn't. The question here was, are these post-processing techniques ready for operational implementation? So a very direct question. And interesting enough, it was kind of mixed. They really liked seeing just the raw data. They liked the spaghetti plots. But the maximum, I thought the maximum would be kind of interesting, but they just, partially because it was too high, you just get really, really, ridiculous amounts. So there's some of these issues that you can then report back to the researchers to work on. You're probably aware of the SBC Mesoscale Convective Discussion, and they do Mesoscale Convective Discussions for heavy rainfall, but they're fairly rare. I mean, the focus of the SBC Service Center is on severe weather, and rightfully so. Of course, HPC, our focus is on these heavy rainfall events. And so we're working with SBC, we're working with Hazardous to actually create in an operational way these mesoscale precipitation discussions, very similar to the mesoscale convective discussion, a focus of the 1 to 6 hour period highlighting which particular counties or areas of a state are most at risk for these extreme rainfall amounts. They're event-driven, so they're not schedule-driven. The weather doesn't work on a schedule, of course. And focused on alerting partners in the media, such as you, where the environment's particularly becoming favorable for these flash flooding events. We have a question here.
Yeah, I wondered how this might change your interaction or your communication with local weather service offices, if this will alter that relationship at all.
Well, I think it would. We're going to have to be in close concert with them, of course. We have chat systems in the weather service that we can go back and forth with. So, this, in a large way, is for the WFO, alerting them to where the National Center is seeing, a particular risk. If they're focused on the severe weather problem, and this often happens, you focus on the severe weather problem, you can kind of get blindsided or, blinders on with severe weather, and you're, forgetting that these supercells also have heavy rain with them, and they keep, training over the same area, and you can get into a flash flood. So to kind of remind them that, well, there's actually a flash flood threat developing here.
I can answer to some respect with SPC's Mesoscale Discussions. When we hear from the field offices, they often say, you don't do them enough. You can't write enough Mesoscale Discussions, and so there's there's a need for that. And if nothing else, you're confirming what a forecaster is thinking in the field, maybe prior to a warning or even during an event. So we often hear, send them out as often as you can.
Yeah, and I think that's an important point too, is even if you have an ongoing event, sometimes you want confirmation that, well, it continues to be favorable, or it looks like conditions are starting to stabilize and it should wind down. I mean, that's important information that you want to know when you're in the heat of an event. So this particular discussion, they were looking at the WRF 4-kilometer NSSL high-res run. So the forecasters through these testbed activities, they're starting to use this new guidance, and it's starting to translate into these new services. We are hoping to begin this experimental product in this spring, so stay tuned. So we go back to these QPF services. So now we have a whole new desk that we can add on to here with this mesoscale precipitation discussion. But one of the missing areas is maybe the medium range prediction. Maybe we can give a better heads up further out of the possibility of these extreme events. And so this is a study by Schumacher and Davis in 2010. They looked at about 9 of these multi-day big heavy rain events. These are the 500 plots and then the observed rainfall from these systems. Some of these are tropical. Some of these are just your synoptic big events. Some of these are convective events, ridge rollers and such. On the right here is the skill in terms of Breyer skill score for these different events. And at the day 5, which is where we're currently predicting these events, HPC goes out to 5-day. Well, honestly, there's a whole variety. Again, this really low skill event was a June 2008 event, looks like. So again, one of those warm season events. There's another warm season event, I think, in here as well. But for example, the dashed black line, this is Gustav, a very good QPF forecast, high skill, extending out quite a ways. And so perhaps for some of these events, we do have some information. And so we're moving out to the day 7 time frame in an experimental fashion. I believe the PNS should have just gone out yesterday, or maybe the day before, but we're moving out on that. The skill, it's not going to be great, but perhaps for some of these events, you can highlight, some of the potential aspects. Just on the lower left here, this is a 5-day forecast for the Nashville event from the European. This is the probabilities of greater than 2 inch. And you can see the black outline is where it was observed. And, the European had a pretty good, more than 50% chance in about the right area. This is at day 5. So there can be some predictive skill going quite a ways out. So if you go to our webpage, you'll find the days 4 and 5 and the days 6 and 7. And then you'll find these 5-day totals and the 7-day totals. Here's an example on the lower right. So, it can provide these answers, or at least a first guess, for questions of the flood threat Or, particularly now with the drought, governors and water resource managers, they want to know when is hope coming, and perhaps just through this quick graphic you can start to get a sense. So it kind of provides a heads up. This is an example of an atmospheric river 7-day forecast. Basically, jumping up and down, saying big events coming, and it did. I believe that's a car. Okay, so we've completed now this full suite of HPC QPF services, from the medium range to the traditional QPF desk, including the augmentation of the probabilistic products, down to the very near term. So that's where we're at as of the state of HPC right now. But communicating uncertainty, which is probably of most interest to you, is the remaining critical challenge we haven't discussed yet. So, you can have the expert perspective. This is from the National Research Council 2008 report, Completing the Forecast. Uncertainty is thus a fundamental characteristic of weather prediction, and no forecast is complete without a description of its uncertainty. So some pretty strong words. You can get the pundit perspective. This is Yogi Berra. It's tough to make predictions, especially about the future. Okay. And then you have the public perspective, perhaps. This is honest weather forecasting. Don't really know. Sorry, not a clue. Might rain, not sure. How many of you can relate to customers when you start to hedge the probabilities, getting that kind of backlash, if you will? So how do we reconcile, particularly the expert perspective and the public perspective here? I don't know if I know, but one of the ways in our test bed that we've been thinking about this is actually incorporating this question in our test bed activities. So for example, for our winter weather experiment last year, and as we're doing it this week, we asked forecasters to give a mock briefing to a non-meteorological decision maker. So an emergency manager necessarily, or a mayor of some town. And then these briefings were reviewed in real time by a social science team, the Wexham team that the Weather Service has been working with. And one of the key points that they made is kind of thinking about communication in terms of a pyramid. As scientists, I keep talking and talking here, providing all this background, and maybe you're wondering, just get to the point, Dave. How many times have you talked to a scientist maybe thinking that? We like to provide this background, then we provide the supporting details, and then we finally get to that result or bottom line. Probably in your business, you're more familiar with the pyramid on the right. Newspapers, for example, have the headline, big bold, font. Just give me the headline, probably your top of the newscast. What's your first sentence, type of headline or teaser. That's the bottom line, right? And then when you have your opportunity to provide the, why does it matter to your customers, and then providing those supporting details. This is hard for scientists to, to kind of switch the way that we talk. And so that was their main, really, recommendation to us. So one of the things I think we talked about here, they also noticed that the briefers, we struggled to differentiate between projecting authority, that, I know what I'm talking about, you should listen to me. And so you kind of fall into this kind of deterministic, kind of giving you the answer, versus conveying your level of confidence. It's kind of two contrasting ideas. You want to sound authoritative, you want to sound like you know what you're talking about. At the same time, there's uncertainty with what you're saying. And so their advice was, discuss those most likely impacts first. That's that top bottom line, give them that top information. And then you can relate the possible alternatives or, dig for more information, the uncertainty of the situation. So I think the point here is the integration of social science into the Weather Service communication aspects, and trying to better communicate or find a way to communicate the uncertainty. A question here.
I'm struggling with the result about communicating the most likely impacts first as a recommendation. Not because it's a very good idea, I get it, but your talk is about extreme events.
Right.
So extreme events are rare, and have high impacts, and therefore invoke another logic, which is to be prepared, you need to present perhaps those outliers in a way that is responsible.
Right.
But in your talk, when we looked at the most likely forecast and compared it to the tail of the distribution,
Yeah.
and we saw that the tail actually represented conditions as they were observed in a very realistic way, it just makes me ask then,
Right.
how can you turn that back around and say we have a responsibility also to communicate unlikely events?
Right, and so I think it gets at those scenarios. So in that example, perhaps, I mean, typically the most likely situation is you're not going to have an extreme event, but you ought to provide those alternatives. And here's an example from the recent Christmas Day snow event over Oklahoma, which of course was a real challenge here. And this was probably the true state of, he has forecast 1 here, mostly dry, windy, and sharply cooler, which was pretty much what occurred. I guess it was cloudy. Or forecast 2, massive life-threatening blizzard. I mean, the true state of the uncertainty was that. Greg, I asked him to look up the DC area for the snow event coming up here. And I mean, the most likely solution is no snow, but there was a member of a foot. I mean, if that system's just a little further north, there's probably that 1 in 20 shot of a pretty good crippling snowstorm up there. So, oh yeah. So anyways, so these alternatives is an approach. Sure.
That's exactly what our news directors don't want. Exactly. They want you to own it. They don't care if you aren't quite sure. They want you to pick one and own it and go with it. Not all of them? Really? Really? To show it?
And then what I feel is probably likely.
Okay.
Sorry, all stations are different, but it just depends on the news director / boss that you have, because in many cases in our area we're very split by the freezing line, and so I have to give different scenarios because that's just how it is in the wintertime. I can't own just one forecast, and that's going to make me wrong in the end if I just pick one and not say that there are variables that might change along the way.
Well, maybe let me show. So here's another example. I don't know how your news director would respond to this. This is the capital weather gain out of the Washington Post. And what they did here, it might be hard to see in the, they had pie charts here for different areas of the metro area. So north and west of the Beltway, inside the Beltway, and then south and east of the Beltway. And they looked at kind of the probability of an inch, probability 1 to 2, 2 to 4, and 4 plus, for example, in terms of a pie chart. I don't know. It might depend on, it's a way of providing alternative solutions. As a snow lover, of course, I was south and east of the Beltway, and we got about 2/10. So that's one way. I mean, I think in media, it's starting to occur. I think instead of just showing that one deterministic solution, my sense is the tide's turning somewhat, and there is recognition that your viewers can handle kind of these alternative solutions and maybe different ways of thinking about probabilities. Here's another example from, this is Bob Ryan, kind of looking at percentages and the impacts, probability of the impacts of, for example, are things going to be canceled? And in this particular event, he was saying a 1 in 10 shot, so most likely not, but a 1 in 10 shot.
Say, news directors aside, I think the viewers, they understand this uncertainty much better than we think they do. And in the digital age we live in, whether we give one deterministic forecast or not, they can go online and find every extreme of that forecast they want. So they know that that data is out there. And it's easy to go, there's tons of snow lover forums. I'm on quite a few because I'm a snow lover too. And you have the people that go to the most extreme. And then you have the people that are always, what I call the snow trolls that it's never going to snow. I'll believe it when I see it. Right. So that stuff's already out there. So I think you kind of do a disservice by not laying out that stuff to the viewers to say, here's what we do. And in a consensus or an ensemble forecast, the best course is usually to take something down the middle, between the extremes. But there's always, you lay out, this could be a foot of snow, so they know.
So I think that's the conversation, amongst your community of how we, and amongst the weather enterprise really, but how we can best, work together to make this happen. It's harder than that, though, unfortunately. Here's the bad news. Forecasting the weather is hard enough. Forecasting the impact, I mean, there are so many factors, that you may not even be aware of regarding the impact. I mean, if you forecast a heavy snow event and then the plows pre-treat the roads, maybe there is no impact then. It snowed what you said, but the roads are actually in pretty good shape. So we're drawing to the close here, just to make this point. So imagine you had a forecast like this. This is a map of terrain. This is the Minneapolis-St. Paul metro area right in here. It's like a 4-inch and an 8-inch. Say this is from the NAM. What are the kind of impacts you'd want to maybe lead with your broadcast for? What kind of impacts you think you'd have in a situation like this? So, here's Minneapolis, St. Paul, maybe some
Be a major snowstorm, right?
We're going back to rainfall.
Rainfall.
So imagine, 8 inches, that's a pretty
major flood.
Pretty massive event up there in a metro area. What would you be kind of leading with here? Right. Water, be really careful around the roads, all these type of things. But we know that there's error, right? We said that 100 to 150 mile error. What if the forecast was down here? Remember, this is a map of terrain. What might you be talking about now? Right. Maybe mudslides? I mean, you have some pretty hilly terrain in here. I mean, 8 inches.
Dave, can I ask how many hospitals, elementary schools, residential homes are in the 100 and 500-year floodplains?
Yeah, exactly. Right. That's where we need to get to. So this was a devastating, historic flash flood in southeast Minnesota. That it occurred in the hilly terrain. They had mudslides, which are just tremendous. And so, and in this case, it was south of Minneapolis, St. Paul. So if you had led with that, highlighting the flash flood threat in the metro area, don't go under these flooded underpasses and all this, forecasting the impact is just incredibly difficult. So to get to your point, Greg, we're starting to kind of work on this in terms of, this is a USGS tool. And what it's pointing out here, in the bottom left here, it has these scenarios. The shelter requirements, how many displaced population, the number of households that would be displaced, the short-term shelter, residential property losses in millions, total property losses, business interruptions. So they're mapping this. They know for this particular small area, this is Iowa City, they're kind of doing a pilot. You know all this infrastructure, where it is, at what elevation it is. And so this is for a minor flood, looks like about 450 displaced households. So I'm going to go to a moderate flood. You start to see on the map here some areas that weren't inundated are now inundated. You're now up to 655 households displaced. Let's go up to a major flood, over 1,000 households displaced. And a record flood, we're talking over 2,000 households displaced, $250 million in damages. So you can kind of play. You can move the stage, if you will, to these different levels. So that's getting at this, the critical information that you probably want to know. The next big step is then if you knew the probability of the river stage, so you had the probability of the rainfall, then you somehow get that into the river flood model, which has its own issues and uncertainties, and you kind of get to the probability of at what stage it's going to be. You can then map that to the probability of, for example, how many houses are going to be affected. And so for a emergency manager in this hypothetical situation, there's a 1 in 10 shot of over 1,000 houses being affected if you know, in this hypothetical situation. These are the types of decision tools that I think are going to help those evacuation decisions we were talking about on Monday and Tuesday. We're not there yet, but I think we're starting to work on these types of decision aids as things evolve. My last slide here is kind of this integration of the kind of meteorology, what I'm familiar with in the weather side of the house, and then NOAA's moving out with a national water center down in Tuscaloosa, Alabama. They're starting to build this center, and this is really getting at kind of those hydrologic aspects, improving the river forecast models, reducing or quantifying the uncertainty with that, and getting at these decision aids and aspects, inundation mapping, which I know is a key thing that we need to do. And so we're starting to kind of build this integrated national weather and water resource for the nation. So with that, extreme rainfall events are challenging. If I can leave you with one thing here, the probabilistic guidance, I think it can at least improve your situational awareness, help your customers and viewers kind of understand what could be possible. And I think these test beds were starting to improve and address these different issues, particularly improving the models, these probabilistic approaches, and communicating uncertainty. And we're starting to work together, the weather and water communities, to really get at the integration of how we can improve quantify and communicate the flood risk and impacts. So with that, I guess I'll open it up for questions.
Does anybody have any other questions? And if you do, please use the microphone so the online audience can hear your questions. And please also identify yourself.
Dave, Greg Carbon, SPC. Real quick, couple of questions on the beginning of the talk. You call this a deterministic QPF forecast, and you may have said it, but is that a blend then that the human forecaster basically uses the guidance to come up with, right?
Yeah, it varies by forecaster. I think the forecaster is looking at all these different individual solutions, the ensemble information, and at least in our national center, they are actually drawing kind of isohyets of the precipitation.
So it's sort of an ensemble to begin with. So deterministic from the perspective that it's one person's decision to send this out as
most likely. What they're targeting is the most likely precipitation amount.
Given their experience.
Yes.
And another question was the atmospheric river. Is there a meteorological definition for that, or?
Yeah. There is, and I probably should know it.
I don't know it.
Certainly the Ralph papers.
Yeah, and it's some distance of precipitable water.
I think it has to do with the water vapor transport.
Right, okay.
Above some threshold. Yep.
And then one last one. The example you showed with respect to the Arkansas flash flood event was quite mesoscale in nature and also terrain induced. And so I know we have PRISM data in the West or across the country. Are any of the HPC QPF products incorporating that into these
particularly in the West, we do can downscale with PRISM. PRISM has its own issues too, of course. Right. Depending on the flow, it's not. If it's not a climatological flow, you're going to get into issues. But particularly in the West, in the East, the PRISM data set doesn't really, it doesn't really pop out at you.
Yeah. I don't even know. I didn't look at it with the terrain in that area, but I know that the terrain played a huge role in focusing that event.
Actually, what we're finding, even the Atlanta event, was partially driven by terrain
and urban development too. Yeah. Thanks.
Well, in Atlanta too, it was the setup before the main event.
Antecedent conditions matter.
Exactly. That was huge for Atlanta.
Yep, absolutely.
Dave, I have a question about, this is Dave Jones with Storm Center Communications. The one graph you showed of the inverted pyramid with, that shows a real difficulty in having scientists really boil down the situation into what are the impactful events. I read the Hurricane Irene assessment.
Sure.
And that was quite critical of HPC's communication to FEMA and others, probably because of this this approach. Are you taking steps, and if so, what steps are you taking to try to help your forecasters better brief, those? Because since you are the backup to NHC,
Sure.
you should communicate, I guess, as clearly as NHC.
Right. I think it's a broader issue. I think it's a Weather Service issue, and I'm looking at Chris, but I think we have to educate our staff, our federal meteorologists, how to better communicate and do decision support. And it's not going to happen overnight. I think through these testbed activities where we're bringing in the social scientists, where we're bringing in their colleagues to kind of, serve as an audience, if you will, you can kind of get it's a learning environment. And so I think we're learning. It's an evolution of the National Weather Service to move towards decision support. Chris, looks like you want to add?
If I may, Chris Strager, National Weather Service. One of the things that we're doing on that, and we've started this out in Kansas City at the training center, we've actually run a few classes, and we're calling it, some people cringe at the name, but we're calling it Decision Support Boot Camp. And we're taking the folks from the forecast offices that are making these types of decisions and talking with the customers, and we're putting them through boot camp, if you would, for DSS. And it's not just the blind leading the blind internally. We're bringing in emergency managers from around the area to come in and critique. How did you relate that message? Was it an effective communication of the true hazard that's out there? So again, you can't change a culture in a month. But I think we've taken some concrete steps now, and we've had some fantastic feedback. And the good thing about this is 122 offices, 13 river forecast centers, these folks come out, they get this great training, then they go back to their home station, and then it's like the Queen Bee type deal where they help bring people on their station on board. So that's one, Dave, to just answer one of your questions, that's one concrete way we're trying to help change things.
Let me I'm sorry, Jim White, University of Colorado. It's interesting to work at that intersection between science and humans because there's all sorts of crazy stuff that goes on there. And it's also interesting in this room because you've got people like yourself and myself as well who think a lot about what the public needs. But there's the folks who are here on camera also have to think about what the public wants. And that's where it gets really interesting to me. And it also is a challenge to us from the science side. What do we provide? I mean, we sort of predetermine in our heads what it is that people need. Whether or not that's right or not, I don't know. But certainly what they want can be something totally different. They may, for example, just look at what's on primetime TV. If I had to program primetime TV, I would program it differently because I don't think it's that good, but it's what people want. They want catastrophe, they want death and destruction, and whether you deliver it to them or not, well, you're not delivering it to them, but you tell them about it. That's sort of in the back of their mind what they're following and what they want. So how far do you take this social science experiment? Are you in the business, for example, of shaping the public, educating the public, or whatever you want to call it? Or are you in the business of giving the public what they want and what they need?
We probably have, there's a variety of opinions, I'm sure. I think the National Weather Service, to our heart, is a scientific and service organization. But core is the science. And our credibility is what folks look to. So, I guess to me, it's I would lean more on the science side. Now, Chris might lean a little bit more on the services side, but I think it's an evolving question. Yeah.
I think it's a fundamental question. It's a sociological, fundamental question. And I think this is the sort of thing you get different answers in different countries and different societies.
I was going to say, I wish I had the answer to that. Do you give the people what they want? Do you give the people what you think they need? Wow, I think it's a little for column A, a little for column B. I think we have a responsibility as a National Weather Service to give the people what we believe is going to impact them, to keep them out of harm's way, or to help emergency managers make decisions, to give you all information so that you can clearly communicate to the public what is going to be affecting them. That's a great question, and I don't have the answer right now, but I think in us, and Dave, I don't know if you'd agree with this or not, I think over the past 5 to 10 years, we've started going to giving people what we believe they need in terms of the impacts, and I see that trend continuing. But well, what's the old saying? Give the people what they want.
No, those ratings are not.
John?
John Morales from WTVJ in Miami. In the NAS study, Weather Services for the Nation Becoming Second to None, there was a lot of emphasis on precisely that, trying to become second to none, particularly in regards to modeling. And one of the things thrown around in the NRC committee was, what would happen if, in the interest of better data assimilation, and therefore a better or more accurate model output, we were able to lighten the load, if you will, of just the sheer number of model runs that are run daily at NCEP, which is enormous as compared to a place like ECMWF.
Sure.
On your end, at HPC, would reducing the number of runs of, say, the GFS to twice a day instead of 4 times a day, would that be cataclysmic to you? Could you not be able to operate in that environment? Again, considering that, in theory, you would assume that with better data assimilation and running it twice a day, we'd have a better accuracy in the model.
Yeah, I mean, the system is the way it is for a number of requirements. I mean, for HPC, I'm not entirely sure that we need the 6 hourly. I mean, perhaps, but so I think there'd be some impact. But for some other centers, there is a particular impact. The National Hurricane Center feels strongly that having those 6 hourly is important. So, everything that NCEP does, we can point to a particular requirement that the Weather Enterprise and American Public has requested, and with verifiable requirements. So, it is a challenge, and I think NCEP is looking at how do we most effectively, most optimally use the limited computing resources that we have. But it's really difficult there is a constituent for every single model and data set that is provided. I mean, in some regards, that's the diversity of the American Weather Enterprise that is unique in a lot of ways to America and could be viewed as a strength. So the investment in computing resources, though, is a critical enabler that would allow us to do maybe better data assimilation. So I don't know that I answered your question, but I think that is a huge challenge right now of how to optimally design and use those computing resources.
I don't think there is an easy answer to it, but I just thought it'd be helpful to bring it, to discuss it openly here, because I mean it's something that, as we move forward, is going to have to be looked at. I mean, either we get more computing power, or we cut back on the sheer number of runs that are being run every day.
NWP is the backbone of weather forecasting today. It is. So investments in NWP will translate into improved forecasts.
Dave? I'd like to just bring it back around to the communications part of the challenge. A few years ago, I was involved in a social science group talking about how to convey risk and hazards and get people to act the way you'd like them to in these events. And I've always been a big fan of analogs. And we don't have analogs for the most extreme events, obviously, but we do have a historical record now, and maybe Ned could talk to this too with the Climate Center database, where we can look at particular forecast scenarios and relate them back to events in the past and look at those past events with respect to their impacts. And not only that, plant the seed in people's minds, perhaps, who experienced similar events in the past, and bring a forecast event to their attention because they've experienced something like that before. It's something that I keep coming back to in these conversations when we talk about how do we convey the risk when we really don't know the outcome. But often if you can find some similarity to a big event of the past, hey, I remember that. I remember what that did.
I mean, we'll have a diverse view on analogs, I think, probably in this room. I mean, was there an analog to Sandy?
Well, no, I know, and I said that extreme events
can break down, right? Is every event can be unique. But yeah, I don't think the community has come to consensus on the use of analogs.
Dave, excuse me, Dave Jones with Storm Center. I'm wondering, I've heard used the term a lot, seamless suite of forecasts. Can you just explain what that is briefly, just so everybody understands sort of like the direction that NCEP and HPC as part of NCEP is heading to really deliver a seamless suite of forecasts?
Right. Well, it's an ongoing process. I think in the modeling world, it's kind of an Earth system modeling framework. Okay, if you think of it that way, where you have the climate aspects are the same system that's used for the global forecast, which is used for the same system as you get down to the mesoscale, which is used for the ecological forecasting, tied to the rivers and how that affects the ecology. I mean, that's the dream, is this one Earth system modeling framework. I think relates in the modeling world to seamlessness. I think in the services side, seamlessness is that, regardless of where a customer goes, they're getting a one authoritative, consensus answer to the particular forecast challenge. Looks like Chris wants to add on here.
Just say, and again, from my perspective, it was more from an operational part of what I did at an FO for years. But one of the things we were criticized before, and rightly so, were our aviation forecasts in terms of the TAFs, the terminal aerodrome forecasts. About one forecaster would make them up, and the other forecaster would do the grids. We're changing that now, and I know in several offices now, we're actually dropping out at least draft TAFs from the grids. So it's a seamless, consistent product. The same 7-day forecast drives outlooks for the rivers that are going out to Corps of Engineers and other customers in that watershed. So I think we're getting to that point now. I know it's much better than it used to be. We still have a ways to go, but especially with the aviation aspect, I like the way that now we're starting to tie them in really to our grids, so that when we make a change in our grids in the short term, it's going to be reflected in the TAF as well.
Ways of maybe reframing some of these issues. One is the probability of false negatives is an important maybe graph to look at and set of plots on the map.
Yep.
A different issue which you were getting to with the USGS flooding and the number of homes is the risk of that type 2 error on lives and property elevates the need to communicate those improbable events, I would think. So one way that NCDC has done that is with their snowfall index, for the climatology of snow events, is looking at societal impacts of snow events, so that you can actually pinpoint in the climatology record where there have been high dollar values associated with snowfall, so that you can kind of put the climatology in a societal perspective immediately.
Yeah, how about a forecast Northeast Storms Index?
Right. I mean, we haven't observed Northeast Storms Index. I mean, maybe just one concluding thought here. I mean, what hasn't come up here is cost loss models, right? Where if you know the economic, political, social, all the factors that go into, for example, an evacuation decision. If you know the cost of evacuating, and then you know the cost of not evacuating, and you know at what threshold, is it a 1 in 10 chance, a 2 in 10 chance, a 3 in 10 chance, where you kind of balance those costs, and that includes political, social, and all these other kind of fuzzy aspects. That's an objective way of looking at, when do you pull the trigger? If it's going to save more money, save lives, I should point that out, by evacuating at a 1 in 10 shot, even though it's going to cost me money to do so and some political capital and such. But over the long run, it's the benefits outweigh the the cost, then that's the level at which, you know, if there's a 10% chance of a 12-foot storm surge in New York Harbor, I better evacuate. So, you know, the cost loss models, I think, is another area where we haven't really discussed yet, but that's another growing area that I think gets at these aspects.
Great. Well, please give Dave another round of applause. Thanks so much.
Thank you. Thank you. Great. Thank you.
Thank you. Okay, that brings us to the end of the first session, and we're going to take a 15-minute break. For those of you watching online, we're going to play a little a video from Breckenridge, so you can enjoy that, and then we'll be back at quarter after the hour. And at that time, we'll hear a presentation from Dr. Jennifer Francis on how the melting Arctic sea ice may be impacting the synoptic weather patterns down where we live. It's a fascinating talk. I hope you join us online. I know everybody in the room is excited to see this presentation as well. Jennifer was one of the most popular YouTube video accesses after last year's summit, and so we decided to bring her back. She has some new stuff. So we'll see you back here in about 15 minutes, and for those online audience viewers, take a look at Breckenridge. What you're missing, have to come out and visit sometime.